Here are solutions to homework set number 10 for ECE 376. This homework set looks at Timer1 Capture and Timer1 Compare. In Timer1 Capture, I'm going to record measure a capacitor. In Timer1 Compare, I'm going to detect whether I can tell the difference between two frequencies. So starting out with Timer1 Capture. Timer1 Capture measures the time between two edges. So what I'm going to do is use a 555 timer and measure the period. So if I have a 555 timer, like here, here's my 555 timer, here's my capacitor I'm trying to measure. The resistors are 100K, 100K, C varies. The period should be R1 plus 2R2 times C times log of 2. Doing some computations, solving for C. C should be that number times T. If I have a 10 megahertz clock, then the number of clocks is 10 to the 7th times T. Plugging it in, C is 0.4089 N picofarads. If I count every 16th edge, it'll be 30.056 femtofarads. So that's my scalar. I'm going to count how many clocks go by in 16 edges. That number times 30.056 is the capacitance in femtofarads. Small numbers. The C code. I just have timer 0 running in the background for no reason other than to run in the background. Timer 1 is running, counting every clock. Prescalar is 1. Capture 1. On every 16th edge, Capture 1 kicks in. I'll record the current time, record the previous time, and the time difference. I'll set up timer 0 for prescalar 1 for no reason other than just to have timer 0 running. I'll have timer 1 running, prescalar 1, and capture 1 is set up for every 16th rising edge. The main routine then is every time N1 gets updated, I'll update by femtofarads. That number times 30.056146685 is the value in femtofarads. Displaying it times 6 gives you the value in microfarads, or nanofarads, I mean. So here's what that looks like. Here is a 1000 nanofarad, or 1 microfarad capacitor, 1000 nanofarads. It's reading as 1030. The light is blinking every time I see an edge with a 555 timer. Every 16th edge, it updates. If I take a 0.1 microfarad capacitor, or 100 nanofarads, that's 100 nanofarads, which is 101.46. There's a little bit of noise. I'm reading this down to 30 femtofarads, but there's noise in the circuit, so this isn't that solid of a reading. If I put two of these together, I should get 200. A little bit of noise. So I've got a capacitance meter that's reading capacitance really, really accurately, down to 30 femtofarads, plus noise. So it's really accurate, but then it's also not all that accurate because of the noise in the system. So to test this, I'll toggle RA1 every timer 1 interrupt, and the net result is 13.106 milliseconds. So basically timer 1 is running the background correctly, but measure 2 millisecond square wave. Kind of one way to do that is timer 1, right here. Let's measure RC0 that comes from timer 0. Seems to be that the time is measuring correctly. with that I can start measuring some capacitors. So here's a 1 microfarad capacitor. Its mean standard deviation 0.1, 0.082. So it seems to be a fairly accurate capacitance meter, measured to a certain number of decimal places. Problem is there's noise. I've got lots and lots of decimal places, but the noise level is kind of making that last decimal point not quite as meaningful. So anyway, that's using Timer1 Capture to measure something like a capacitance. Next, let's look at Timer1 Compare. Timer1 Compare will output a 1 or a 0 at a precise time. So I'm going to do that to output a precise frequency. The question I'm asking is, can I detect a 1% change in frequency at 440 Hz? Now to do that, I'll set up a double-blind experiment. I'll play the first note, 440 Hz, and the second note will be either 440 or 440 plus 1%. So here's kind of what it looks like. I'll start the game. And those two different notes. But the top button, if I think it's different, I was right. That was different. Different. Same. I've got my little frequency counter right here. That was 444, 445 Hertz. Same. Same, 440 Hertz. Same. 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 There it was. See, the multimeter or frequency counter saw that difference. So that's kind of the idea. I'll try to do that without using the frequency counter. Now to write the code for that, I'll first need to set up Timer1 and Timer1 Compare. So Timer1 is always running in the background. Compare1, actually Compare2. If I'm playing a note, I will toggle a pin and set up the frequency every N2 clocks. The main loop is going to sit there, wait a second, toss a coin, take Timer1, and with 1, that's my coin toss, 1 or 0. I'll set the frequency to 1444, or 444 Hertz, and turn on the note for half a second. I'll then wait 200 milliseconds and then check. If my coin toss was a 1, I'll play a different note, otherwise play the same note. Play the second one for 500 milliseconds, then check. If I hit RB2, I'll clear the count. Otherwise, if the button I hit corresponds to whether the coin is right or wrong, I'll record whether I was right or wrong there. So RB2 is a clear. That cleared my count, and I missed it. Let's try it again. We'll turn this off, so I can't cheat. That was different. I was right. Different. Different. Same. Same. Different. I'll get this one wrong, so that was the same, but I'll hit different. Okay, so that seems to be working. To test it, what I'll do is I'll write some test routines. So this will always play 440 Hertz. This will always play 444 Hertz. Measure the frequency, and it comes in as 440, 444. You can solve that on the meter here. Check my random number generator. Every time I flip a coin, I'll print out the answer. Here's the ones and zeros. There are 25 zeros, 28 ones. From a chi-square test, that's basically a coin toss. No pattern apparent. Now let's go back to the question. Can I tell the difference of 1%? So here when I'm trying it, I was right 15 times, wrong 3 times. Chi-square score is 8. From StatTrek, that means 99.5% chance I'm not guessing. Apparently I can hear the difference of 1%. And that is homework set number 10 for ECE 376. And that's Timer1 Capture, Timer1 Compare. With Capture Compare, I can record events down to 100 nanoseconds, which is really, really impressive.